Hello, we are Ragin'Aero, and this is our submission for the simulation competition for the 3D printed aircraft competition. This is the 2023-2024 Ragin'Aero team. Pictured is the team with Leviticus, our final design, at the intramural fields where we practice with our plane. Organizational structure, I am Logan Petrie, the CAD supervisor.
I am Bryce Anderson, the Computational Analysis Director.
And the rest of our team is Garrett Dewitt, our team lead and communications director, Thomas Nguyen, our project manager and electronics and software director, Matthew Walker, our fabrication, testing, and finance director, and lastly, our faculty advisor, Mr. John Carroll. Project constraints. We have to maneuver our aircraft within a 360 foot by 225 feet area and stay under 35 feet in height. We must use strictly 3D printed technology, except for our electronical components, propellers, and assembly hardware as well. And the aircraft must stay below 55 pounds. This is given to us by the FAA regulations, Title 14, Part 7. The aircraft must only use 8 seconds of propulsion at the very beginning of flight. No combustion, propulsion, or lighter than air is allowed, and it must be either launched by hand or under its own power. Pictured here is Matthew Walker launching our plane at one of our tests with Leviticus. Our goals and purposes is to design and manufacture a fully 3D printed aircraft to sustain flight for the longest duration. We're allowed 3 separate planes for competition. So due to this, we don't really care if our plane lands and stays intact. So we made to make our plane as light as possible and increase glide time. We decided it'd be best that it's okay if the plane gets destroyed every single flight. So that's why we have multiple. We're planning on having multiple planes, and we plan on them crashing every time. We want to design the planes to fit within the constraints of the 3D printers. The 3D printer bed is only so big, so we have to make sure our parts are able to be printed on there while being as big as possible to reduce parts on the plane. And our last goal is to have a flight longer than 27 seconds to win. This was gotten from last year's winning run in 2023. This is here pictured is our Prusa bed. Our Prusa is the main printer that we use for to print all of our planes on. This is just a bunch of our parts on the bed to show that this is our constraints, and this is how big we have to make our parts. And on the right is our sliced exploded view of our Leviticus, our final design, actually our third design in SolidWorks. We have 3 designs. Mark 1 is Genesis, Mark 2 is Exodus, and Mark 3 is Leviticus. So this is a video of that exploded view and animation of it in SolidWorks, showing all the pieces that we have to put together. All these pieces are printed on our Prusas. We also have Raise 3D Pro 2s that these white wing sections are printed on, and the black in the back is carbon fiber, which is printed on MakerBot Method X printers. So our end product is to fully develop an aircraft that will glide efficiently with and without propulsion. It's good, when we have the weight and a big battery for propulsion, but whenever that motor cuts out, we have to also be able to glide without it as well. We want to integrate a functional and user-friendly control system within the aircraft. None of us were hobbyists or anything beforehand. We're all pretty new to the RC plane field, so we had to make it user-friendly for ourselves to understand and easily to troubleshoot as well. And here's a beautiful picture of our final design, Leviticus. Leviticus's mass is 1.8 pounds. That was measured right before our last flight, and its dimensions, its wingspan is 55 inches, and the fuselage length is 37.25 inches. Those are just general dimensions right there. Going into our airfoil selection and more of the technical stuff, we chose the AG24 as our route and the AG27. We chose these airfoils due to their high lift, low drag, and them being thin with no camber. We really wanted to have no camber to reduce our drag. And the AG24 was chosen on the route because of its wider width. As you can see on the left side, the AG24 shows it's a little bit wider, as you can tell from the AG27, which is our tip. These are the graphs we got from airfoiltools.com, where we also got all our tools from. So we used airfoiltools.com mainly to get all our airfoils. We looked at all these graphs as well as the coefficient of lift and drag versus alpha as well. That's how we went through every single airfoil in its database and compared every single one and got the AG27 and AG24. So this shows at our angle of attack that we got using CFD of 6 degrees. We'll talk about that a little bit later. This is the lift and the drag coefficients. So very high lift, very low drag. And going on to our stabilizers, we chose NACA 0012 and NACA 0008 for our vertical. We chose these ones symmetrical. They don't have to produce any lift, so we chose symmetrical. And the 008 was chosen for the vertical because that one is going to be on the top, so it would have as little drag as possible. Going into our calculations, we used the generic lift equation to find what our minimum lift should be. It was based off our weight of the aircraft of that 1.8 pounds. We got 8 newtons of force. So we know when we go do our CFD and our calculations of our wing, it has to be more than 8 newtons to keep the plane in the air. And our aspect ratio, we wanted to have it for gliding characteristics. We wanted a high aspect ratio, which is normally typical for gliders, very long wings, very thin, very small chord lengths, but very long wingspans. And we also got our first fuselage length 4 to 6 times the wing width. We got that using this NASA document on general aerodynamics. So starting with our first two designs, the wings are pretty similar from our first design, Genesis, and our second design, Exodus. So the wings were 50-inch wingspan, 6-inch 3-inch tip chord length, and tapered polyhedral. So that tapered, we got our plan form was a tapered or trapezoidal wing. We wanted this because it has better lift distribution than the rectangular wings in the middle of Figure 13. We had the trade-off is our stalling characteristics aren't as ideal as in a rectangular. We still have um, the stalls from the root instead of the tip. However, we're not using ailerons, so it wasn't that important for us to have different stalls since we're not going to have any flight control surfaces on the wing to worry about stalling. So we went with the trapezoidal design over the elliptical because the elliptical would be a little bit harder to print and harder for manufacturing. In the polyhedral design shown in Figure 14, we have two different angles. The middle section is at 0 degrees, then it goes up to 3 degrees, our long section, and our tips at the very end go at a 20-degree angle. That was so whenever our plane wants to roll, it'll correct itself, and we don't need ailerons. Our wing loading was pretty high at 17.84 ounces per square feet. We got that down later with Leviticus by increasing our wing size. We'll get to that later. And our fuselage length, using that NASA document, we got 40 inches in length and a modern glider design. That just basically means it was pretty big in the front and it kept getting smaller and very thin towards the tail. So our center of gravity was very important, and the main thing we struggled with this year, it must be located within 25 to 33% of the chord length. As another rule of thumb we got from NASA. So Figure 15 shows our second plane. That little pink origin shows where our CG was. That cutout is where our wings would go, and it's a little far behind. But that was just the fuselage and not all the components together. That got brought forward later. And Figure 16 just shows how we have to have the CG in front of the neutral point to make sure that our plane is dynamically stable throughout flight.
So one of the other issues that we had this year was when we were using some of our motors, we were faced with two choices: either using the fixed prop on the left or the foldaway prop on the right. We first tried out the fixed prop on the left, and whenever we were trying to slowly land it and glide down, that prop would provide some drag. And then also, if the prop was in the wrong position when we would land, it would grab the ground and the entire plane would nose over, causing a catastrophic crash. So we went with the foldaway prop, or we tried to use it, but the foldaway prop, because there was a metal nose cone, wouldn't allow our motors to go all the way to 100% due to the rotational weight required to spin that prop. So on the next slide, we see that we have developed, or we reverse engineered that metal nose cone, and we made a 3D printed version of it, so that this version would be a lot lighter and would allow us to spin those motors that we are using for our planes to spin that about 100%. Um, and the structure of the nose cone would be able to withstand the rotational forces of the motor as well. So we could see that on the next slide we have a video of the motor going to 100%. So with using that 3D printed nose cone, we were able to successfully test to see if it was able to withstand 100% of the motor, and it did. And we plan on using that in our final iterations of the aircraft that we are designing.
So going on to more of our design of the airplane, we notice our this is our section 4, the fuselage picture. This is the very last part of the fuselage that goes from the aft of the wing to the empennage, or the front of the stabilizers. So we noticed for our first planes that we printed this out of lightweight PLA, and it was bending a lot due to our servos being in the empennage. We brought them all the way back, so where our control rods were very small, we had a lot of quick reaction from there from the transmitter, and had more control and didn't have very long rods running outside the plane. So we had moved our servos to the back, and that a lot of weight in the back caused that lightweight PLA to bend a lot. So at first we had used fishing line to tighten it up, kind of what some old planes would do back in the day, but realized that was against the rules. So we decided to print that these sections with carbon fiber. Now we usually printed this with the Raise 3D Pros, and those are 15-inch sections, but we can't print that with the Prusas or the Method X that can print our carbon fiber. It has the right nozzle. So we had to make this into 3 sections, section 4A, 4B, and 4C. And we made that with carbon fiber, and our bending went away almost completely. It's still there a little bit, but not nearly as much as lightweight PLA, thanks to the stiffness of carbon fiber. Going into more now, starting our CFD. This was for Leviticus. The very top was what our first original design was, version 1 of Mark III Leviticus. So we noticed that at the very behind that green origin where it starts to bend, there was this fluid separation. It's kind of yellow orange. There was a lot of flow separation right there. So we wanted to get rid of that to reduce our drag. So we came up with version 2 and version 3, 2 different designs and iterations we wanted to test throughout CFD. And using CFD, we inputted some parameters. I believe it was 15 meters per second. And using this coefficient of drag equation, we inputted the coefficient of drag in SolidWorks and got that, plugged this into the equation to get our drag force. And you can see from version 2 and version 3, we got these different drag forces, and eventually went with version 3 to the lower drag. Now, the numbers are not very different, but our plane is pretty small to where any small change in drag force will make a big difference overall. And going into our last plane, the wing plan form, this is Leviticus. We decided to increase the wingspan by 5 inches, and the tip chord length would go up by 1 inch from 3 to 4. And instead of doing the polyhedral, we had a lot of problems with both sides of the wings were not symmetrical, and I was causing roll, and it actually did a barrel roll throughout one of our flights. And we wanted to make sure that every plane was symmetrical from here on out. So to help assembly, we basically made this massive flat section, and then the tips were the only piece that went up, and they went up at a 15-degree angle, and that helped a lot with we got our wings symmetrical every time, as well as it still counteracts that roll motion and keeps our plane level. Our wing loading, by increasing our wings, went down to 15.8, which from 17.84 was a very big difference. And our fuselage also got reduced by 2.75 inches from 40 to 37.25. This again was to help with that bending of our empennage in the back. This is what we use to find our center of gravity for our plane. The left, this yellow part, we inputted with our measurements of our wing and our horizontal stabilizer, and this purple in the bottom left, we got the calculator inputted out. So the important number is that red one from wing root leading edge to center of gravity. That's the money number that we have to hit in SolidWorks. We have to make sure that our center of gravity is exactly 2.65 inches on our plane. And we also got our tail volume ratio V-bar that says how effective our horizontal stabilizer is. 0.63 is pretty high, but we want a very effective tail to where we have a lot of reaction when we're flying up there. Then we put this wing area, our estimated weight, and our max lift coefficient from our AG-27 airfoil at 6 degrees, and we calculated our wing loading as well as our stall speed using all throughout this calculator. We got our CG and everything else we need. This was for assembly. This is our slot and pin wing slice connection. We made this to help a lot with assembly. At first, we had this little jig where we were going to fit our whole wing sections in, and they'd meet in the middle. and we were going to resin them from there. But we decided we're going to have this pin and wing connection. It slides right in, and it works really good. It reduced a lot of time off of our assembly.
So initially, we wanted to test out doing CFD on our airfoils just to see the characteristics that we could see to expect during actual flight time. So for the 2D cut plot of Genesis, which is our first iteration of the plane, it was more of us just kind of getting a feel and seeing, hey, is our airfoil going to actually generate lift at any sort of speed? So on this first cut plot, it's the cut plot of pressure, and so we can see that low pressure at the top, which is in blue on that scale at the top left, and then we can see the high pressure occurring on the bottom of the airfoil itself, which is in terms of how you generate lift. And then on the next slide, we can see the cut plot of velocity. Now, if generating velocity, you want a higher velocity on top and a lower velocity on the bottom. And so we can see we have that higher velocity of the 12.48 meters per second on top, and then the lower velocity of around 8 or 9 meters per second. And then towards the trailing edge of our airfoil, we can see the velocity dropping down to almost zero. So this would be kind of where your drag is occurring, and then everywhere else is where your lift is happening. So here is where we start getting into the actual kind of technical approach. We're kind of more familiar with CFD, and we're getting more familiar with analyzing how air is flowing over our wings. So we took the velocity of 22.5 meters per second, and then the angle of attack that we chose for our two airfoils that are on our wing, the AG-24 and AG-27. So the 22.5 meters per second came from the velocity that our motor, the thrust that our motor was producing, so the wind that it was throwing over our wings. So we took that and then threw it into here. And so here we can see a 2D cut flash of the pressure. So we can see that high pressure occurring, a big bulge of the high pressure occurring on the bottom, which is generating a good bit of lift. And then the low pressure on top, that kind of small bulge of pressure right there. And then for the velocity cut plot, so keep in mind the velocity it's in the negative direction. So the dark blue is actually your high point velocity, and then the top is our low point velocity. This was due to how the wing was placed in SolidWorks with the origin. So we could see the velocity flow going over the wing, still the same thing where we have the high velocity on top. Now it is a little bit slower than what we expected at first, but this is why we changed our design and moved on to the dihedral design with the wingtips going up with that flat section in the middle on the next slide. So here we see the pressure come out of the pressure. So now that looks like that looks better with what we wanted to see. So still the same inputs. This is more of what we wanted to see with that high pressure on the bottom and the low pressure on top. So the low pressure is a little bit bigger of a we do have a good bit of more high pressure on the bottom, generating more lift for this wing, and also a more stable airflow as well. And we'll see that with our cut plot of the velocity. So the cut plot of the velocity, we see a more stable airflow, higher velocity up top, very low drag from the air in the back, and then almost kind of staying in the high velocity region there with our 2D cut plot. So here we have the lift versus the graph of Leviticus. So this was imported from SolidWorks into Excel. So that first region where it kind of goes above, like it's around that 25, that goes above 30, and then kind of goes to that nice planform line right there, or streamline line. So that first section is where SolidWorks is kind of converging on a solution. But then whenever you get down to that actual line right there, that's where your actual lift force is going to be. So that's around like 28 newtons. And then if we go to the drag force graph of Leviticus, same exact thing. You're having your little convergence right there, and then that straight line where you have your drag force about like 0.1. something. So we could get our max values from that, and from what we saw from doing our CFD on Exodus and Leviticus, we saw Exodus had a 23.87 Newton lift with a drag force of 0.65, and we increased that lift with Leviticus by changing the design to we increased it by 25.14% to get a 29.87 newtons of lift. And then the drag force, it decreased by 75.23% to 0.161 newtons. Now, it doesn't really seem like a good bit of difference, but keep in mind, as Logan said before, our plane is small, so any small difference is actually a significant difference in the RC world. And thank you for attending our presentation.